Okay, you may still remember using a slow clock is one of the ways or one of the strategy to actually reduce your power consumption or your current consumption. Okay, and we say that the current, alright, the current is equals to 1 over the clock frequency plus a certain constant. Alright, so the clock frequency normally they will give you, alright, and the constant they should also give you, or otherwise they will give you straight away the value. So in this case, they actually give you the amount of hertz, the amount of frequency, they also give you the current straight away. Alright, so therefore you don't need to calculate anything. Alright, so using this information that we have had from the previous video, alright, let's start with a question. I think this is pretty much like an exam questions. Alright, so a data logger is using based on a SEM3X microcontroller, runs at 1.8 volt. Alright, and takes reading every second, and it takes about 250 instructions to process and store data. Alright, so 250 instructions is within one period. Please take note, later on we'll talk about it. Alright, and these 250 instructions are 250 instructions per cycle. I will highly assume, but I may be wrong, so be careful of that. And what is the best approach to minimize the average current? Alright, so over here, if you were to use this frequency, you will have this amount of current. If you use higher frequency, you have a larger current required. Alright, so we want to actually find a way to actually minimize the average current. Alright, just to take note that we are already using a slow clock, a slow clock in our SEM3X already. Okay, is that we are trying to furthermore improve and also to prove to you that the sleep is a good strategy to be used to help you decrease your current consumption. Alright, your current consumption. Okay, so please take note of that. So there is 4 ways, and these 4 ways will illustrate to you what's the meaning. Okay, so the first way is you run your clock or your system continuously without sleeping at 84 megahertz. So you are just running. So in this case, you are just running flat. Alright, you are just running flat for 84 megahertz. Okay, or in other words, you are just using 80 milliampere straight away. Alright, so this is the time domain, this is the current. Alright, so you're actually using 80 milliampere throughout continuously. So this is actually given to you in the previous question. Okay, although we also didn't calculate anything, it's straight away give you one. So you just take and whack only. Okay, so straight away you know that if you run continuously, you're just only simply taking in 80 milliampere. That's the answer, finish. Okay, for the second one, it will run continuously at 0.5 megahertz. Alright, so 0.5 megahertz is what? 16 milliampere. So it's running at about 16 milliampere, continuous running also. Alright, but however, you are as you can see, the lower your frequency, this frequency is your clock frequency. Alright, so the lower your clock frequency, alright, the lower your current consumption. You see, it's mega, it's times 10 to the power of 6, this one is times 10 to the power of 3. Alright, so the lower your frequency, the lower consumption your current will be. Alright, so this is something that you also want to know. So please take note, please take note, please take note, please take note. Alright, lower frequency, lower current. Alright, please take note. Remember. Okay. So the next part comes in slightly to be a little bit more tricky, is that you sleep between your readings, then you process the data at 84 megahertz. Alright, so what does this mean, and how do we do this already? So this is more on the sleeping side. Alright, and we're going to calculate the sleeping. Alright, previously we were actually doing the calculations for the running continuously. As you can see, running continuously, you're constantly taking in 80 milliampere and 60 milliampere. With regards that you have already used a slow clock, alright, it's already one method to minimize your power consumption. But nonetheless, let's talk about the third one, which is with sleeping. Alright, so it says that if you remember, we have 250 instructions. Okay, so one period, for example, this period is equals to, alright, 1 over your frequency, alright, times your number of instructions. So this is one equation that you also may want to take note. Alright, so please take note, blah 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 blah. Anyway, So in your frequency, your operating frequency is actually your clock frequency, which is 84 megahertz. So you just take 1 over 84 times 10 to the power 6 times 250, you'll get what? Alright, you'll get about 2.9 microsecond. Alright, normally we just write as 3 microsecond. Okay, so for 3 microsecond, alright, you are taking in 250 instructions. Microsecond is very small. It's 3 times 10 to the negative 6 seconds. Alright, or you can also say that it's 3 times 10 to the negative 3 millisecond. It's really small. Alright, 1 second is how much? 1 second is 1000 millisecond. Alright, so comparatively you can see the level of negligibleness. I don't know what the hell, but anyway. So how can we draw this thing? Or how can we visualize this thing? Alright, so I'll just simply draw out the graph. So this is your time, this is your current. Okay, so firstly you can take in 250 instructions. Okay, so 250 instructions you actually use about 3 microsecond. I'm gonna be very exaggerating. So this over here is your 3 microsecond. Okay, while this particular magnitude, alright, it's 80. Is it 80? Yeah, it's 80 milliampere, right? Because it's shown over here for 84 megahertz, 80 milliampere. So actually currently we're processing the data using 84 millihertz. Right, so we have about 80 milliampere. Alright, while the rest, please take note of that. I'm gonna exaggerate a bit also. Is that you're gonna take in a less amount. So the rest of the time you're gonna sleep. Alright, the rest of the time you're sleeping. Okay. Maybe I should draw this line first. Okay. So this portion over here is when you're sleeping. Okay, and when you're sleeping, you're actually taking in current also, but it's very negligible. Alright, it's what they say that take the current to be 3.5 microampere when in backup mode to allow for other components. The backup mode means that you're talking about the sleeping mode, I would say. Alright, so 3.5 milliampere is over here. Alright, it's very exaggerated because this is milli, this is micro. You see, I purposely draw it to be this thick so that you can see properly. Okay, so therefore over at this side, this whole length is when you're sleeping. Alright, and therefore this whole thing over here is your 1 second. Okay, so what it says is that the microcontroller SEM3X runs at 1.8 volt, takes a reading every second. So you take in 250 readings or 250 instructions every second per reading. Alright, so per reading it takes in 250 informations within this particular 80 milliamp. Or the rest over here, alright, takes in a slight current to actually run other components, but it's really negligible. Alright, so this whole thing is 1 second. Alright, so the next round, the next period, then you actually rise up again, you take in another 250 another 250 instructions, then you sleep again for another 1 second, then you wake up again. So this whole thing, including this one, is 1 second. Alright, so it's like you can say that this thing over here is your 3 microsecond, as I have said over here. Alright, this whole thing over here is your 1 second minus away 3 microsecond. Okay, so this whole thing is actually 1 second. So the next round again, you can take information, blah, sleep, and then that thing. Okay, therefore what I have been drawing all along is actually drawing this thing over here. Okay, so now I'm gonna explain to you that what is the average current if I were to so-called sleep and awake. Alright, so I'm gonna paste this thing over at this side. Alright, so now we can officially use this thing already. Alright, how can we do this? Alright, within this particular 1 second, okay, this portion over here, if I were to shade it, this green color one, is when you're asleep. Okay, maybe I should use the same color, at least you get the feel. Okay, so it's actually asleep. while the portion over here is when it's awake, right? This portion over here is when it's awake. You see? This particular 3 microsecond. Okay? So when you're awake, this means that you're actually taking in data. Alright, taking in the 250 instruction. Alright? So you 80 milliampere multiply by your 3 microsecond. Right, what do you have? Over here I would have 0.24 microampere second, because I'm taking milliampere times microsecond, so the unit should be in terms of ampere and second together, so I have ampere second. Alright, maybe not lah, okay, I forget already, but anyway it should be 0.24 milliampere second. Alright, because milli times micro, alright, 10 to the negative 3 times 10 to the negative 6. Oh, it's actually nano. Alright, sorry, my fault. Alright, so it should be 0.24 nano ampere second plus 3.5 times the 1000 millisecond. You can say that this 1000 millisecond over here is this portion over here. Alright, is 1000 minus 3 microsecond. Or this is actually 1000 millisecond. Alright, minus 3 microsecond, which is negligible. You still get back 1000 millisecond. Right? So therefore this whole chunk over here is still 1000 millisecond. Although we say that this thing over here is 1 second or 1000 millisecond also, but however this portion over here is so small until that in decimal place you can still say that 1000 millisecond. I think you get what I mean already lah. Right? Like this is 1000 for example, if I show you 1000 times 10 to the negative 3 minus away 3 times 10 to the negative 9. Right, this thing over here is this one. This thing over here is this one. Alright, so take a look about it. Alright, eventually if you take this thing minus away this thing, you are still getting back this one. Right, because this is 10 to the negative 9, very small, super ultra small. So therefore this 1000 millisecond is telling you that it's actually talking about this portion over here. Alright, when you are sleeping. So that's as they say, this part over here is asleep, this part over here is awake. Alright, so if you were to multiply by this factor, so I will get back 3.5 microampere second. Okay, because 1000, if it happen that 1000 times 10 to the negative 3 second, for example, is equals to 1. Alright, 1 second. It's the same thing. Alright, so apparently I'm actually multiplying this thing with 1 second. Okay, so it's just 3.5 times 1, that's all. Okay, so therefore it's just 3.5 microampere. If you don't understand what I mean, you just write down on the paper, you just do yourself, you can understand already. Otherwise you just skip a few seconds ago and then watch again. Alright, so over here I have 0.24 nanoampere second plus 3.5 microampere. So what I can do now, in fact I just realized that this is not 0.24 nanoampere second, damn it. Alright, 80 times 3 is what? Is 240. Multiply by milli times micro is what? Milli times micro is times 10 to the negative 9 ampere second. Okay, and actually should we write this 3.5 microampere as 3.5 times 10 to the negative 6 ampere second. Alright, and this whole thing is going to divide by 1, right? Because 1000 times millisecond, milli is actually negative 3, right? So this will be 1 second, because our SI unit are in terms of seconds, you see. So therefore, alright, we can actually, so the SI unit over here, if I were to just take note of the SI unit, alright, so this whole thing divided by 1 second, you're going to cancel out the SI unit. Alright, so what I would have is 240 times 10 to the negative 9, alright, ampere plus 3.5 times 10 to the negative 6 ampere. Okay, and I can rewrite this as 0.24 microampere. Alright, if I were to change it to micro, which is minus 6, so I'll times 1000, divide by 1000. Okay, is it divide? Yeah, I should divide by 1000, so it becomes, I'll leave you a link about this is just math lah, okay? the conversion, I don't talk about it, you just take note lah, alright. So 3.5 times 10 to the negative 6 is actually 3.5 microampere. So if you were to add up together, you will have 3.74 microampere. Okay, so this is how they calculate this one over here. Alright, so over here this is sleep dominant. Why is it sleep dominant? Because the ampere that you sleep, alright, the amount of current you take in is when you sleep is larger than the amount of current you take in when you are taking in information. You see, this is the point where you're awake. This is the point where you're asleep. When you're asleep, the current is taking in more current than your awake one, alright, then it's considered a sleep dominant system, because you sleep more than you take in information. Alright, so this is what it says lah. And more on the proof is that when you sleep, you take in more current than when you're taking in data. Alright, so when you're awake, you take in data, you're actually using current lesser than when you're sleeping. Alright, so this is just a way of saying things lah. Okay, so this is the third one. Alright, this is sleeping between readings, then processing the data at 84 megahertz. So last but not least, sleeping between readings, then you process the data at 0.5 megahertz. Alright, the fourth one. So in fact, we should actually write this as the fourth one. Okay, so the slides actually have a different numbers. But anyway, the first step first is that we need to determine, alright, the time for taking in information. Alright, the same step as we have done earlier in our previous parts, right? We actually determine our period. For one period, we take in 250. Alright, so we're gonna use this formula again. Alright, so at least this will make you feel very familiar. So in this case, our frequency is what? Our frequency is 0.5 megahertz. Alright, so I'll just simply sub in as 0.5 times 10 to the power of 6. Okay, so if I were to calculate this thing, we have realized that this 0.5 megahertz is wrong. Okay, it's because in fact we're actually running at 125 kilohertz. Alright, previously, and the third part we talked about 84 megahertz, right? So we sample at 84 megahertz as what we have said, processing the data at 84 megahertz, correct? And in fact, 0.5 megahertz is something that we don't have the data. It's this thing over here. This is the second one, we should say when you run continuously at 0.5 is wrong. Or it shouldn't be 0.5, it should be 125 kilohertz. Alright, so over here this is 125 kilohertz, then you have 16 milliampere. So same thing over here, if I have a 125 kilohertz, then what do I have? So I'll just sub in as 125 kilohertz. Alright, then I would have 2 millisecond. Okay, so this is the 2 milliseconds. So in other words, if I have the time over here, and this is my current, alright, my magnitude of my current, okay, at what? At 125 megahertz, 125 kilohertz, 125 kilohertz, alright, then you're talking about 16 milliampere. This is what we are showing you, right? You're taking in 16 milliampere. Okay, so therefore I'll just show you all over here. So this is at 16 milliampere, alright, for 2 milliseconds. Okay, for 2 milliseconds. So you take in 250 instructions within this 2 millisecond over here. Alright, and then over here we operate in what? We operate in, where is the question? We actually operate in where? In 3.5 microampere when in backup mode. So when we sleep, we actually have a 3.5 microampere. Okay, so over here this is actually 3.5 microampere. If you were to compare just now in our previous graph, alright, same thing, we have a 3.5 microampere over here. This is the 80 milliampere from our clock average current, or clock current, okay, not average anyway. But anyway, so this is how we draw. Alright, and over here this is up to here. Alright, so this distance over here is actually 998 millisecond. because 1 second is equals to 1000 millisecond, correct? So therefore so this whole chunk over here is your 1 second. So within your 1 second, 2 milliseconds is used to take in 250 data or 250 instructions, while the 998 millisecond is used to sleep. Okay, so for each of the second, alright, you will have this information. So for the next second, and then you're gonna talk about another 2 milliseconds, and then you sleep for another 998 millisecond, and then so on and so forth. So each of this thing all over here is 1 second, 1 second all along. Okay, same thing we're going to calculate again. We take in 60 milliampere, alright, times my 2 millisecond. Okay, and then I add it up. So this part over here is my awake, alright, while I plus with my asleep. So asleep I have 998 millisecond, okay, times, alright, 3.5 microampere. Alright, this whole thing all divided by, alright, 1000 millisecond, or 1000 millisecond. Okay, or you can say it's 1 second, because everything I think we should write as all 1 second. Alright, so therefore if you were to do this math, alright, I would have 16, let me see, 16 times 2 is actually 32. Alright, milli times milli, which give you a micro, because milli is 10 to the negative 3 times 10 to the negative 3, so you'll get micro, 10 to the negative 6. Okay, so the SI unit is in terms of ampere second, because there is ampere and there's second over here. Alright, plus, alright, 998 times 3.5. Alright, what do I have is, so 998 times 3.5, I will have 3493. Alright, in this case I should actually write it as round off as 3500 times, alright, milli, this is millisecond, alright, multiplied by micro. So milli times micro is actually nano, so I would have a actually I should write as over here, because 998 times 3.5 is this one already, so this leave up is only the SI unit, so it's nano is 10 to the negative 9, alright, and then ampere second, okay, divided by 1 second. Okay, so the second will cancel each other, so what I would have is 32 microampere, alright, plus 3500 nano ampere. I can change it to, alright, so 3500, alright, I can divide, so 1 2 3, sorry, I should how should I write, yeah, so it's 1 2 3, I will have 3.5. okay, so therefore I have 3.5 microampere. Okay, just math only lah. So if you were to add up together, you have 35.5 microampere. So therefore what I've been written is all along this thing over here. Okay, so this portion over the 60 milliampere times the 2 millisecond is when you're talking about the awake system. Alright, which is talking about this thing. Alright, when you're awake. Alright, then for over here, this thing over here is talking about this system when you're sleeping. Okay, so when you add up together in terms of average, alright, be mindful that you're going to divide by 1000 millisecond, because all this thing happens within a second. Alright, all this thing happens within a second, so you need to divide the seconds also. Alright, so this is something that you need to take note of. Alright, nonetheless you get 35.5. And over here, as you can see, the awake part, this whole thing over here, is taking in more current than when you're asleep. Right, when you're asleep, you're actually taking in 3.5 microampere, while when you're awake, you're actually taking in 32 microampere, which is kind of a lot. Alright, if you were to compare this value 35.5 with our previous one, this is 3.74. Alright, so that's what we have calculated just now, alright, just a while ago, is 35.5. Alright, is when you have a 125 kilohertz. This thing over here, this value, if you still remember, we're actually calculating in terms of what? We're actually calculating in terms of 84 megahertz. Alright, so if you were to compare comparatively, okay, maybe I should write it down properly. This is the findings that we have found. Alright, so this is when you're talking about 84 megahertz. Alright, you're actually using 3.74 milliampere only. However, if you are using this is also 125 kilohertz. Alright, so if you are using 125 kilohertz, you're actually using 35.5 milliampere. Alright, so the frequency actually, the lower your frequency, actually increase your ampere. Alright, it's a little bit different from the scenario when you're continuously running it. Okay, when you're continuously running it, alright, the lower frequency, the lower current. Alright, so when you're continuously running it, the lower frequency, lower current. Okay, however, when you're sleeping, alright, you want that the faster frequency, the lower current. You see, 3.74 milliampere, this is 35. You see, this is 125 kilohertz. Okay, so this is a lower frequency but higher current. This is a higher frequency, a lower current. Alright, so what does this mean over when you're sleeping? So this meaning tells us, sorry, this should be micro. Alright, this also should be micro. Alright, so the conclusion is that sleep as long as possible. Okay, then get the processing done as quickly as possible. Alright, because the processing means that your frequency over is processing very fast. So you process very fast, then you sleep more. Correct? So this is what it means, right? Because over at this third part, alright, we actually process using 3 microseconds. Comparatively, you will talk about just now, alright, we actually process 2 milliseconds. Right, because our frequency is kind of lower in this case, in the fourth case. Right, when you are using 125 kilohertz, you are using 2 milliseconds to take in 250 data. If you are running at so high speed, alright, at what is it? At 80 megahertz over here, alright, then you're actually taking in 3 microseconds. You're actually using 3 microseconds to take in 250 data. So therefore, this conclusion is very powerful, is that sleep as long as possible, alright, then get the processing done as quickly as possible by increasing the frequency. Alright, this is only applies when you're sleeping. Alright, so yeah. Nonetheless, for these two cases, alright, these methods are still very good because they are in terms of micro ampere, which is taking a very little ampere only. Or comparatively, if you are dealing with a lot of data, the third one is actually something that you want to consider. Alright, run things faster, so then you can sleep more. Okay, so this is the conclusion that I should present to you, and this is a very long video. Alright, so see you soon.